first things first. I want you to understand states of water. Now, when we're talking about clouds and things, we're talking talking a lot about how water changes from solid, liquid to gas, and gas, liquid to solid, and back and forth, back and forth. Clouds, water cycle, this is very relevant. Now, we'll start off with some very simple ice. Simple ice. If you leave ice out on a counter in the room today, what's it going to do?
Melt.
Where does the energy come to melt it from? What heat? The ambient temperature in the room has enough energy to melt the ice. Well, how much energy? Well, about 334 joules, according to this chart, per unit of ice. You apply heat to the ice, turns to a liquid. Okay, no big deal. But what do you have to do to get it to evaporate? Same amount?
Nope.
No, according to the chart it's not. I mean, look at this. To make that ice go to a liquid, 334 joules. To make that new liquid now go to gas, starting from where it was, 2,500 joules. Are we to get? It's almost 8 times as much energy to evaporate a liquid as it is to have it melt. And the same is true in the reverse. You release 2,500 joules when the gas condenses, and you release 334 joules when it's frozen. So, examples of this. Hot, sweaty day. You're outside doing hot, sweaty things, and the wind hits you. What does it do to your skin when you're all sweaty? Okay? It cools your body off. What's actually cooling your body off? Well, the wind is hitting the sweat, causing it to evaporate by adding energy to it. Actually, well, I'm not going to say that. The wind causes it to evaporate by just going over it, evaporates. Okay, 2,500 joules per unit is absorbed into the water, into your sweat. As the sweat evaporates off, all of that energy, usually in the form of heat, is absorbed and taken away. Where did the heat come from if it's sweat on your skin? Your body. So thus, we call this evaporative cooling. When something gets hit with wind and you're wet, it's cold. Okay? So, you evaporate and the heat is absorbed. Okay, that's an example with your body. How about an example with the earth? Where does the earth receive the most direct sunlight? The sun. Thank you for answering the equator. Okay? The equator receives intense amount of solar radiation because it's the most direct. Now, all of that radiation hits. Most of the equator is around what land or water? Water. Ocean. So all of that ocean water is going to get warm. It's going to evaporate. And a lot of the energy from the sun goes up into the clouds, and that heat is transferred from the equator into the clouds and then pushed other places by wind patterns and dumped somewhere else. Beautiful example of this would be a hurricane. Hurricanes form in the tropics closer to the equator. They get really hot. They start to rotate counterclockwise in the northern hemisphere, and they smash into North America. And they bring with them quite a bit of energy from that heat. And they dump all that energy and all that warmth and all that wet stuff on, for example, I lived in Kentucky when Hurricane Ike came through Kentucky. Okay, Louisville, Kentucky, we lost power for 2-3 weeks from Hurricane Ike. So there's a lot of energy that was transferred from the tropics, and all that heat was transferred to the middle of the United States. Okay, so this is the basics of how this whole system works, how heat is exchanged. Okay, now we need to talk about something else. Let's talk about water. Water specifically in the air. We talk a lot about water in this class. Okay? So in the air, there is water vapor. In the room right now, there is water vapor. Okay? Lately, the temperatures have been hanging out right around 0 Celsius. What is 0 Celsius in Fahrenheit?
30 degrees.
32, right? That's the temperature that water freezes. Might be really helpful to understand that as you go into the next test. You have to read a thermometer. Okay? Alright, moving on. At 32 degrees Fahrenheit or 0 degrees Celsius, personally, I don't like the Celsius scale for measuring the temperature of the air, but science uses it. I think that Fahrenheit is a much more descriptive scale. So we're going to be flipping back and forth, but you need to be able to understand both because all of science uses centigrade Celsius. So if we're at 0 degrees Celsius, 32 degrees Fahrenheit, the air can hold 3.5 grams of water per kilogram of air, or 3.5 grams of water in a piece of air. Okay, 3.5 grams, not a whole lot. Well, that's right now. Last graduation, I was at graduation sweating and hot and having a great time watching the graduating class graduate. But it was really hot that day. It was like 95 degree hot. And that was just in June. Okay. Well, how much water can the air hold at 95 degrees? 35 grams per kilogram. How much more water is that? 10 times more water. Thus, the warmer the air becomes, the more water it can hold. The colder the air becomes, the less
so dry in winter.
water it can hold. What was that?
Why it's so dry in winter.
Why it's so dry in the winter? Specifically because we have really cold air outside of the building, and the building sucks it in through the HVAC system and warms it up. So any moisture that's there, which is very little, now feels even more dry because now the air can hold more water in the building. So any moisture in the building gets sucked into the air. Thus, the fish tank has almost completely evaporated now. Yes, our nasty fish tank. Okay. Because it's a nasty fish tank. Okay. So, humidity is the amount of water in the air, and you need to know that the warmer the air, the more space. The colder the air, the less space. We're going to illustrate that here by vial, vial, vial. This is the same vial starting at an initial temperature of 20 degrees, dropping 10 degrees, dropping 10 degrees. Initially, this is at what we call 50% humidity, relative humidity. What is it relative to? Is 50% the amount of water in the air? No, it's not. What is it? Well, I haven't told you yet, so if you knew it, that'd be awesome. Okay, it's not 50% of how much water is in the air, but it's 50% how much the air is full. So, if the air can hold 14 grams and you have 7 grams, then the air is half full, right? Not half empty, half full. Okay? And thus, you have 50% relatively humid. Okay? If it was 100% humidity, then it would be 14 grams of water because it can hold 14 grams of water. That would be 100% humidity. Now, we know that if you cool the air off, it can hold more or less water. Cool the air, it has a capacity goes down. Okay, so let's cool it off 10 degrees. We go from 70 degrees to about 50-ish degrees, 10 degrees centigrade. Okay, well, now, by cooling the air off in this sealed jar, the air can hold less water. In this case, now the air can only hold 7 grams of water. Oh good, we've only got 7 grams. Whew. Kind of scary. So, now the air is completely full. Did the amount of water change? No. What changed? The temperature, or the ability of the air to hold the water. So now, The water vapor is 7 grams. The water needed to be saturated is 7 grams. The air is 100% saturated. The relative humidity is 100%, meaning the air is completely full of water. Is that a question?
Yeah.
What's your question?
How come when you have when the water is cooler, it holds less?
When it's cooler, it holds less, because when cold things tend to contract and condense, and it's just not as much room for the water as the air gets denser and heavier from being colder. There's just simply less room for the water to be present. Okay, this is 100% humidity. Now, if this is completely full, and I drop the temperature some more, is there going to be any room for all of this water in the air? There's going to be less room, right? What happens? We come over here. Now we're down to 0 degrees, so we've dropped 20 degrees from our initial. Now, the air stays the same, but I have 3.5 grams of water vapor and 3.5 grams of liquid water. Why? Because the air couldn't hold the water anymore because it got colder. And the water, what does it do when it goes from vapor to a liquid? It condenses. It condenses, and our relative humidity is still 100%, but now I've got some liquid water. Do you guys understand relative humidity now? Okay, do you see what happens to water when it gets cold and cold and cold and cold? What happens to the water vapor if it continues to get colder after it reaches saturation? It's going to condense and come out of the air. Okay. How do we talk about this scientifically? This is dew point. Okay, not DuPont. Dew point. Okay. The dew point, or what is the temperature at which water will condense? Well, if it's 70 degrees in here, there's a certain amount of water in the air. The dew point in the room, I'm not sure what that temperature would be, but it's going to be some temperature less than the 70 degrees it is, where the air and the water reach equal portions. The air cannot hold any more water. You guys might have seen this if you go places where, like, the inside of a house, it just gets really, really cold. Maybe you lose power and you start to see water collecting on the walls. Okay, the house has reached the dew point, and now there's so much water compared to how much the air can hold that it starts to continue to get colder, and the water comes out, and you get dew on the walls, or on the glasses, or on the whatevers. Okay, how do we measure this? We use a sling psychrometer. If I get a chance, I'm really going to try to get us to use these things. These are really cool. So here's a sling psychrometer here. Okay, a sling psychrometer, there's 2 thermometers. One of them's got a little a bulb on it. One of them doesn't have one. And they're both reading about 22 degrees. You take one of the bulbs, get it just a little bit wet. Okay. And I've got like a little piece of cloth on here. Now, what happens if your skin is wet and you're running or wind is blowing at you? What do you get?
You get cold.
You get colder. So if I start to spin these, besides all the water that's flinging off, if I spin this long enough, I'm adding a new kind of feature to the thermometer, and that's the movement of air. And as the movement of air hits that wet wick, it's colder. And I should be able, on the thermometer, to measure the difference. Check that really quick. This is still 22. This one now says 18. Okay? And this is how the experiment works. It's a very simple experiment. And you do it inside or outside. If you do it outside, you can do some graphing with your data and determine how tall the clouds are. That's how we determine how tall the clouds are, because I can measure the rate at which air cools. Am I still at 18? Nope, I'm at 16. Okay? So as I continue to spin this is called a sling psychrometer. Hint, hint, cough, cough. You might see just a picture of this on the test, and you have to give me a description of what does this do. And you're going to tell me, well, Well, we use this to measure dew point, or the humidity of the room. I'm still at 16. Okay, so I could say it's got a difference of 8 degrees, pull out some charts, and I could actually tell you what the dew point is in the room based off the data that I'm getting using a sling psychrometer. Okay? I know it's a crazy big word, but you've got to know it. Okay? So that's how we get the dew point. Now, so we've learned about humidity. We've learned how air, as it cools, can hold less moisture. Let's talk about pressure. Pressure, pressure, pressure. Has anyone in here been to the Chin Center?
Oh,
Chin Aquatic Center? Okay. I would like to say that I'm intimately familiar with the bottom of that pool. Because
Oh, I didn't
About
work off the bottom.
4 years ago, I did my lifeguard instructor training at the Chin Center, and they made me go to the bottom over and over and over and over again. And then someone had to go down and grab me and put me in a spinal position and pull me up. I feel very, very familiar and comfortable with the bottom of the Chin Center. You know how deep Chin Center goes?
Like
15 feet.
It's 14 feet. Close, too close. It's 14 feet. Has anyone been to the bottom of Chin Center's deep end?
Yes.
What does it feel like in your ears?
It hurts.
It hurts.
You have to blow your ears.
Pressure. Kind of like, teachers get at the end of the day with all the students. Pressure.
You have to flap your ears.
Now-
to blow your bellies.
Get the what?
Pressure on your ears, where does it come from if you're at the bottom of the pool? What's causing your ears to hurt?
The water pressure.
The water pressure. Where does the pressure come from? All the water above your head. Literally, like the weight of all of that water above your head is pushing on you. That's why it hurts so much. Because the inside of your head is not designed to be at the bottom of the pool. But if you had scuba gear, you could stay down there long enough and you could get everything to equalize and stay down there long enough and the pain will go away. Okay? This is the pressure, because the inside of your head is pushing out, the outside is pushing in, and when the outside is pushing in more than the inside is pushing out, that inequality is what causes the pain. Okay? So I'm going to equate being at the bottom of Chin Center with standing here at the surface of the earth. Okay? If I'm standing at the surface of the earth, I have all of this air above my head, all the way up, all the layers of the earth, pushing down on me, just like being at the bottom of the pool. Well, if I swim to the top of the pool, more or less pressure? Less, right? Because our ears, thank gosh, don't hurt anymore. Okay? So if I go to the top of the atmosphere, more or less pressure? Less, right? Because there's less air pushing down on me. Do you guys ever fly in an airplane?
Yep.
Okay.
You chew gum.
If you ever fly in an airplane, commercial airliners go above the clouds. And they're flying in between 30 and 34,000 feet. That's pretty dang high. And at 30 to 34,000 feet, there's a significant loss in pressure, enough that the inside of your head now has more pressure than the air outside, and that causes your ears to pop. Okay? Now, when the plane decides to descend, which is always a good thing when planes decide to descend, and you land, you're now going further and further and further toward the bottom of the atmosphere, like going to the bottom of the pool, and then your ears once again start to hurt, because now the inside of your head has less pressure, and the outside of your head has more pressure from the air, and that's why it always hurts more landing than it does taking off, because it's more pressure instead of less pressure. And then if you can't get the pressure to equalize, it's bad. That's why you always chew gum when you're on airplanes, because it allows your eustachian tubes and everything to clear it out. Okay. Now that we've had the nice little chat about pressure, air that is rising is exposed to less and less pressure, right? Because it's going higher. Well, when things are exposed to less and less pressure, they tend to expand. And when air expands, it cools off. As it cools off, it's not cooling off because it's losing heat. It's cooling off because it's expanding. And as it expands, it cools. And the opposite is true. If you push it down, it's going to get compressed, it's going to get warmer. Well, wait a second. Didn't we just learn that colder air can hold less water? So does it make sense that if you have a whole bunch of water in the air and it starts to rise, and as it starts to rise, it's starting to expand, starts to cool, will it eventually reach 100% humidity? Yeah, where it's fully, like the air is holding less and less and less and less and less, and before you know it, it's full of water because it's holding less and less and less. It's like the room shrinking around you. It gets to a saturation point. If the air continues to rise beyond the saturation point, you get a cloud. Because it's like the jar, where the jar had all the water vapor, it got too cold, and the water condensed. Well look, the water condensed, and it made a cloud, and it has now. Okay? I'm the only one allowed to be overly dramatic. Okay. Now, have you ever noticed, looking at the sky, driving down the road, pretending that that cloud really is a bunch of cotton candy that you could eat, have you ever noticed that the bottom of the clouds are almost always flat? Has anyone ever noticed that?
Yeah.
Okay, guess why they're flat? Because as that air is rising, that level, that elevation where the bottom of the cloud is the elevation where the air becomes saturated. And everything above that, the air has condensed because it can't hold the water anymore. So it went from water vapor in the air to, whoa, way too cold, not enough room, and the air is just like wringing out the water. Wringing out the water, and the water comes out in the form of a cloud. So if you watch like the still motion or the slow motion videos of clouds forming, they often kind of billow up. It's because a lot of warm air is being pushed up. All that water is getting shoved way, way, way high. Air can't hold it anymore, turns into a cloud. Okay? And you can use charts to measure the rate that air drops, the temperature that air drops. So it goes up for every 1,000 kilometers you go up, you lose about 10 degrees Celsius, or about roughly 20 degrees or so Fahrenheit. Which is why you have glaciers at the top of mountains and not jungles. Because higher in the elevation, the colder it becomes. Okay? We good? You got it? Okay. Alright, I'm going to give you 4 pictures on what causes air to rise. This is a picture of a rain shadow. Orographic lifting. Okay, orographic means somebody put a mountain in the way of wind. What were they thinking? You put a mountain range in the way of the prevailing winds, or the wind, the way the air flows, especially if it's coming from water. The air flows and it hits a mountain. Well, what happens if you're riding a bicycle and before you know it, the entire sidewalk's been turned into a ramp? Do you go through the ramp or do you go over the ramp? Well, sometimes you go through it if it's a bad ramp. But you're going to go over the ramp. Well, the same thing is true. I want to go visit my family in Indiana. There's a mountain range in the way. I've got to go, as I drive, it's just going to push me up and over the mountains. The air goes with me. And as the air is going over the mountain, it's getting pushed up and up and up. It's holding less and less and less because the higher it goes, the less water it can hold. And before you know it, you get all of these pretty clouds. Pretty clouds turn into rain. All of the water is sapped and wrung out of the air, and then instead of really wet air coming over the mountains, now you have really dry air on the backside, and as the air descends, it's even more dry the further it goes down because it's expanding and sucking up all the moisture it can find. So the backside of a mountain range is often a desert. That is exactly why half of Washington State is a desert. That is exactly why. Because the Cascades block in Seattle, but not in Spokane. Okay? So Spokane is a very kind of deserty conditions. That's why if you go to Utah, it's a desert. But if you go to the other side of California, it's a luscious, almost like a temperate rainforest. It's not the temperate rainforest, but very, very wet and rainy in the Sierra Nevadas. Okay? So that's one way. You can push warm air. If warm air is trying to push above cold air, it gets shoved into the air and you get lots of rain. This system that we've had was probably some kind of a warm front or maybe even included front, but probably some kind of a warm front like this. Okay? If you have two wind patterns going head on into each other, one's going this way, one's going that way, they hit each other, there's no place else to go but up. And that creates clouds because the air is being shoved into the air. That gives you clouds. That table needs to be quiet, please. Okay? And finally, what we talked about before, if you heat the air, it rises, and if it rises, it cools, and if it cools, yeah, and so on and so forth. Localized convection. Okay. Cloud formation. Everything we've been talking about has been building to understanding how clouds form and what kind of weather comes with them. Stay awake, Pam. Come on, stay awake. Little gremlins are smacking your chair. Pam, staying awake doesn't mean put your head back down. Come on, head up. Head up or stand up. Okay. Shh. Y'all. Okay. We've been trying to lead up to how do we get these clouds? Well, to get these clouds, we learned here that the air has to reach saturation. Step one to get a cloud, you have to reach saturation. Okay, step two, you need condensation nuclei. I wonder if I can get this to work. You need condensation nuclei. Condensation nuclei is very simple. It's dirt in the air. Could be smoke. It could be ash. Could be pollen. Maybe just some dust. Okay.
What is that?
So I'm going to attempt an experiment. I've seen it done, but I've never done it before. Okay, so here we have a water bottle, and I'm going to do, this is what I'm going to do. I'm going to try to show how you have to have condensation nuclei to make a cloud form. Well, I know that, water in here, you think there's a lot of water vapor in here?
Yes.
Yeah.
Yeah.
If I compress it, that increases the temperature inside, right? Okay, so anyway, if I squeeze it, I should be getting a cloud, and I'm not. What am I missing? I'm at the saturation point. What am I missing? Condensation nuclei. I really hope this works. My experiment's going to look really silly.
Sarah,
Sarah, it doesn't explode. It's just a match.
I can't see.
Okay, let's see if I can get this to work.
I don't
Okay.
think it works.
No, you gotta do it quicker.
You took too long.
You're too slow.
Yeah, you were too slow.
Such an
Yeah, you gotta go faster.
Such an epic
You
battle.
just grab a matching check, you put it in there.
Yeah, I've done it before, it works.
Okay, do it again.
Okay, got it quicker. There it is.
There we go.
Or like,
Dang.
See the cloud form?
Move your head. I can't even see it. I'm right here. I'll see it.
It's kind of hard to see, but it actually did work.
It stinks. We're gonna have a fire alarm.
No, just
now.
make something. How was I gonna make a fire?
Really need to calm down.
I did that with the crab.
It stinks. I can smell it.
What are you smelling? What mineral is that?
Sulfur.
Sulfur.
Yeah.
Someone else.
We use sulfur to make matches.
Stop doing it.
I can put a nacho with myself.
Okay.
Where's the noise?
Oh, you turned on the
What did the match add? Shh. Oi! What is it the match added that caused the cloud to form?
the ash.
It added smoke or particulate. It added the condensation nuclei. So I gave you a little hint here. This is an important slide. You have to know what conditions are important for cloud development. Okay, let's talk about these clouds really quick. Okay, we have approximately an hour left of class. Today's the first day of the elongated schedule.
I thought it was 55 minutes. We leave at 2:10.
55 minutes. Okay. There are, clouds are categorized by their form and their height. Now I'm going to say they're roughly categorized by their form and their height because it doesn't always match perfectly. But you have clouds that are really, really high. You have clouds that are really, really low, and clouds in the middle. The ones that are really high are almost always a cirro cloud. So, in fact, I think they're always like a cirrocumulus or a cirrostratus or just a cirrus
Isn't
cloud.
there
Don't throw stuff, guys. Okay. There's also alto. Is anyone in here an alto? Any of you ladies sing alto?
I'm a soprano.
Tristan. You guys are begging for a sea change. Okay. I am a baritone bass. I tend to sing down in the basement. I can sing tenor if I have to, but I tend to be kind of down in the basement. Okay, so you go from bass, baritone, tenor, and above tenor you get into the female voices. You have alto and soprano. Okay, alto is the middle voice between sopranos and the dudes. Okay, so alto clouds are the middle clouds. It's a good way of remembering if it's guys, seriously, calm down. Quiet, please. Okay, so alto clouds, cirrus clouds are the highest ones, and the low clouds tend to be a lot more stratusy or cumulusy, but we don't have a special prefix for these like we do for alto or cirro. Okay? Now, here I have some puffy clouds. These are cumulus clouds. They kind of look like broccoli, well not broccoli, but cauliflower. Cumulus clouds, just puffy, beautiful. It's a turtle. It's a bunny, right? When you look at the clouds, guys. When you look at these clouds, they tend to be very puffy. They tend to have nice flat bottoms. Okay, those are cumulus clouds. Now, you all can also have stratus clouds. Now this is showing stratocumulus. So let's talk about stratus clouds. Layers of clouds, very overcast. What we've been having the last few days, stratus clouds. When you have stratus clouds, you typically get a really cool prefix or suffix added to the word. Nimbus. Okay, a nimbus cloud is a cloud that is raining or precipitating. So a nimbostratus cloud is what gave us all of that snow yesterday. Okay.
That was sleet.
A cumulo nimbus cloud. A cumulonimbus cloud is a cumulus cloud that is raining. These are thunderstorms. Okay? Why is what? So much bigger? Well, of all the different types of clouds you have, the cumulonimbus clouds are kind of the big boys of the block. Now these are clouds that are, cumulonimbus doesn't have low, middle, top. A cumulonimbus cloud is a thunderstorm. Okay, you get all thunderstorms come from cumulonimbus, and you see these in the summer all the time, right? You look off in the distance, whoa, it's a tall cloud. In fact, it's so tall, I can see it's just kind of like getting really flat on the top. They often call these an anvil shape on the top. Why does it stop up here when it grows? Because it's literally hit the very top of the troposphere where all the water is contained. So as the water comes up this high, it's so cold that the cloud spreads out on top into ice crystals. It's so like negative 40 degrees up here. It's super cold. Now, very top of the troposphere. So these storms are caused when a lot of warm air gets pushed above a lot of cold air in a cold front, and you get thunderstorms. And then you have all the electrons that are so different from the ground because it's all being worked up. You get zap! Lightning.
Whoa.
Okay? Lightning is it's a static charge between a cloud and the ground, a static shock between the cloud and the ground, except it's millions of volts or over 1 million volts. And here's the thing. Electricity's hot. So the air around the bolt of lightning is super heated hot because the bolt of lightning's so hot. Well, Vion, you know what that does?
It kills you.
That creates a tremendous pressure wave of that super hot, hotter than the surface of the sun hot around the lightning, and that creates a loud pressure wave that you hear as thunder. Thunder. I was climbing over a mountain pass, and we were trying to get to, I think, Upper Sand Creek Lake or Lower Sand Creek Lake. We were up in the Colorado mountains, trying to go up. We were at 12,000 feet, hiking, backpacking, everything we owned. We had been in the wild for about 3 days by that point, and we were trying to get over a little ridge to get to the lake. And thunderstorm came in, and probably from here to Miss Grease's room down the hallway, lightning struck. And you see the flash of the lightning, and because I was so close to it, we heard the instant wha-boom of the thunder. It literally knocked me on my butt. It was, whoa! I fell to the ground, and the ground was wet. But we stood up and got to shelter really quick, because we were in the middle of a crazy thunderstorm. I was on the top of Sacagawea Cirque in the Bridger Range in Montana, actually kind of southwestern Montana. The Bridger Range.
You said Montana wrong.
Montana. Thank you. I was up, we were doing some geological surveying, we were measuring the strike and the dip of the layers in Sacagawea, and it started to snow, because we were so high, it started to snow, and then it turned into a thunder snow. So, here in it was a thunder snow, it was snowing, but it was a cumulonimbus cloud, and it was thundering and lightning in a snowstorm. It was only awesome telling it after the case. Well, I was terrified.
So you're telling me that
Okay, have a seat. Let me talk about one more type, and then we're going to take a break. Okay, fog. Okay, fog. Fog. Fog is a cloud that's on the ground. If you guys have ever wondered, I wish I could walk in the clouds, and I promise you, you can. Anytime it's foggy, go outside and you're walking in the clouds. It's the same thing. It's the same thing. A fog is a cloud on the ground. These form for Cole, shut up. These form usually when you have cold air over warm water or wet air over cold ground. Typically wet air over cold ground is what we get here, or if you have a pond or maybe the Aquapond Reservoir can get like that steamy fog above it. I have been in the mountains and driven into fog so thick that I literally like driving in my Ford Explorer, and like maybe from here to the edge of the first stripe of the board was the edge of the car, and then from here to the small bookshelf was how far I could see in the road. Okay, why was I driving? Because I couldn't get off the road because I was stuck in traffic. And all the traffic was going pretty quickly in very thick fog, and the problem with thick fog is you can't see where you're going. And that's why you often get these like 50-car pileups because people drive too fast in the fog. But if you slow down, someone could come up and hit me. So it's super dangerous. I was looking for a way to get off the road or out of the fog.
It gets thick because
You just have like bad
it goes down the mountain into the in between the mountains and it gets stuck.
Okay, that's part of it. Okay, I'm not going to talk about rain yet.